Yeah. All right. Let's get started. So my paper is called Automatic Interpretable Personalized Learning. I'm Ethan. Aaron Haim is another PhD student in our lab. He's very pivotal to this. He does all of the communication between what students see in ASSISTments and what my service provides to the students. So very useful. Adam is an amazing statistician, and if you see any stats in this, it's because he knows how to do it and taught me how. And then, Neil is in charge of ASSISTments and lets me actually use real students to do things. So thank you to everyone. And let's get started. So a little bit of background on ASSISTments. It's an online learning platform. Most of you know about ASSISTments, so I won't talk too much about it. This is what it looks like when a student is using ASSISTments. You can see that they are asked a question. They have a button that says show answer. Sometimes they have a button that says show hint or show explanation, and they get to put their answer in and submit. When there is a hint or explanation available, this is what it looks like. This one right here is a hint. It's just a series of messages that they can request one at a time. But for the same problem, here's an explanation. Now, these explanations and hints that I'm showing you now came from an initiative called TeacherASSIST, which we presented at in 2020 here, where we just crowdsourced a bunch of tutoring from teachers. And at the time, we randomly gave students the crowdsourced tutoring or no tutoring. And we were able to show both in that initial study and in a repeat study last year that the crowdsourced tutoring does help students overall, which is like, okay, good. We're not hurting them by just asking random teachers to write content for them, which was a concern because sometimes different tone can have an effect on whether or not the student can kind of follow along with the hints. And then in addition to that, last year we showed that some teachers were better than other teachers, meaning like the hints and explanations that they wrote, students tended to get the next problem correct more often. So we thought, well, hang on. If we know that they work overall and we know that some are better than others, maybe we should be trying to figure out which one's the best. And even a higher goal, maybe we can figure out which ones are good for which students. So you can kind of see this is the motivation in a nice diagram. The which tutoring is the best is kind of this top option where all these boxes are just different tutoring that we could give to a student. And if we just measure the average next problem correctness for every time a student got one of these, then you would say, all right, let's give the orange one to everybody. 72% of the time, students get the next one right. But then we also want to look deeper and we want to say, well, hang on, what if we have these two different groups of students, red students and blue students in this hypothetical? If we have the ability to figure out how effective each of these tutoring strategies are for each kind of student, then we might find something like, well, okay, the orange, which was best overall before, is still best for our majority red students, but the blue students actually benefit most from this purple hint instead of the orange one. So this is kind of the goal. And now I'm going to get into the infrastructure that I built into ASSISTments to accomplish that. So it's a big diagram, but we're going to focus on one box at a time. In ASSISTments, as the student is using that tutor, when they are going to the next problem, they send to my service, which provides us, I guess I should say, the point of my service is to pick the tutoring that we think is going to be the best for the student. So the request comes in. The request just has a lot of identifying information, like what's the student, what problem are they on, what are the available tutorings from our crowdsourcing. That comes in. And then step one of the service is we identify, and this is in real time, right? Every time they start a new problem, we do this calculation for them. We identify the learning environment context, which is features of the student and the problem. So, maybe this is a more difficult than average problem. That was a geometry problem. Maybe the student tends to ask for help before they try the problem themselves. These kind of features, we're not calculating them right now. They're already in our database. I'll get into when I calculate them after I talk about this. But we kind of find all these features of the learning environment. We then also identify the potential student supports, which are those different tutoring messages, and we figure out the features of those as well. Is this a video? Is it an image? Does the teacher highlight different parts of the tutoring with different text color, different attributes like that? And once we have all that context, we pick a model. Now, the point of the service is to be able to compare models to each other. There was a workshop yesterday on A/B testing, and that had a lot to do with testing different, curricula or different support overall. But with this, we really enable the ability to test different models that are working behind the scenes to make these decisions. So the model selection works based on an identifier that's attached to the model. So I could say, okay, this model applies right now because this model is for this particular student, or this model is for this particular problem skill, or this model is for all tutoring that has to do, like all hints and explanations, all of it applies to this model. And so if three different models apply, then we just randomly pick which model we want to use. And that way we have this RCT going on in the background for like, does random recommendation, like how does that compare to a, neural net that was trained on all of our past data, right? Like we can look at these and make a comparison. So once we've picked the model, we give the model the context, which, or features or, covariates, whatever you want to call it, right? There's a lot of words for it. And then the model makes a prediction and estimates which of the available tutoring strategies or student supports, again, lots of words for it, which of those are going to be most effective. And then we send that back to the ASSISTments tutor, and that's the one the student gets. So that's what happens in real time. And then offline, we look every night. We look back at the day's data. We pick night just because, like, most of our students are in North America. So if around 2 a.m. Eastern time I run this update, then we don't lag the server too hard. But ASSISTments records all of the things that students do in the tutor, down to like, at this time they clicked for a hint, then they typed an answer after that, and we can use all of those actions to calculate prior statistics for the students. Like I know what percent of the time the student asks for help before trying an answer, the average time on task for a problem. And I update these averages every night using the day's action logs. So the first thing we have to do is we have to identify in these action logs when the tutoring that we gave to the students were actually viewed by those students, which you can do because there's just an action log for, hey, they looked at the tutoring. And then once we do that, then we go back into our kind of context tables and we pull the context that we used at the time. It's important to not use the current context for the student, because if you're trying to update your model, you need to know the context that the model used when it made its decision. So we store that, we take that context, we calculate the reward, which is, I guess it could be in reinforcement learning, it's called reward because it's kind of a thing that you're trying to maximize. But if this was just a supervised model or something, then it would just be like the thing you're trying to predict. But we get, in this case, it's always how well did the student do on the next problem, because it's a simple metric. It makes sense on like a surface level. Like, yeah, if the tutoring helped, then they'll probably get the next problem right because these are on the same topic. They're usually completing these with an assignment. We wouldn't go to like a different assignment to do like, hey, did they get the first problem on their next assignment right because of the tutoring we gave them on the last problem on their previous assignment? We're not going to do that. That's not a good system. But either way, so we have this, how well did our tutoring do? We have what information would we use to make that decision, and then we just update the model. After we update the model, we go back into those action logs, we gather statistics, we update our statistics, and then now we have new context for the next day, and we just keep going. So I've been talking about model, and now I'll transition to, well, what model are we actually using? What did we try? And we tried multi-arm bandit algorithms, which are a silly name for this kind of algorithm. But I have this little flowchart here so we can all follow along with what it is if you're unfamiliar. Step one, just observe the context. Observe the features of your environment. What do I know about, I'm the bandit algorithm. What do I know about my situation? Well, okay. I have these three options right now. Now we're in box 2. I have these three options in front of me. How well do I think the student's going to do if I gave them each of these three options? And then I make that decision, and then I say, well, okay, then I'm going to give the student this option because I think it's the best option. Here you go, student. And then the student, sees the tutoring. They try the next problem. They get it right or wrong. I say, okay, how well did you do? And then I say, oh, okay, you didn't do that well. I should definitely probably give you a different one next time, or at least I should learn that this one that I gave you isn't as effective as I thought it was, and I've highlighted that last box, this green box, because this is where all the thinking happens. This is where all the fancy, I mean, if you want to call it machine learning happens. And this is a very, very simple Bandit algorithm. This one is one of my favorites because it's just like, yep, makes sense, works, it's nice. It's Thompson sampling. I've added beta Bernoulli because it's a beta distribution and the reward is binary, so they tend to be called that. But this is a really basic model. So in this, you see here, there's only for contextual bandits do they observe the environment. This Thompson sampling model, it doesn't even look at the environment. All it looks at is the prior distribution of reward that it's seen before. So for example, let's assume I have 3 supports. I have a red, blue, and a green support for the students. And whatever happened in the past, each support was given out 10 times. And so you can see the red to correct 8 incorrect, blue and green, correct, incorrect. And I use those correct and incorrect numbers as my alpha and my beta in a beta distribution. And so here are the 3 distributions. And then the way Thompson sampling decides which of these 3 tutorings to give to the student is it just picks a random number from each of the distributions. And then whichever random number happens to be the highest, that's the tutoring we end up giving. So you can see right now, it's mostly going to be giving green tutoring, but there's a good chance that we might pick a blue one. And the idea here is that the more samples you collect over time, the narrower these, like this variance is going to be basically, and like the tighter your margin on what you know the reward to be is going to be. And so you start by kind of exploring many options. Like if we had no information, we would just think that they're all even. But then as these distributions kind of form and separate, you're tending towards making the decision that you think is the best each time. I really like Thompson sampling. I think this is very simple, but very effective. And it is. I mean, there's lots of papers about how it's extremely effective. So that's what we did. We put Thompson sampling in. It doesn't know anything about the student's environment. Even though we're calculating all these features, it doesn't use any of it. We have random selection, which is RS, because we want to compare it to something. We can't just say it works if we don't have a control. So that's what we've been doing so far in ASSISTments. Just if there's multiple tutor strategies, pick one at random, give it to the student. And the other thing we're doing now is the beta Bernoulli Thompson sampling. And you can see that it is really slightly more effective, which is a little disappointing. We would have liked it to be more effective. You can see that out of the about 40,000 times that a student got the tutoring, looked at the tutoring, and then we updated the model with the reward, the actual percent of time that the student got the next problem correct is only 0.3% more. That being said, it is a statistically significant 0.3%. Like if you fit a model where you give a slope coefficient for the beta Bernoulli Thompson samplings reward over time versus just the control reward over time, it is like a statistically significant coefficient, but the effect size here is really small. So, okay, why is the effect size so small? Well, one, usually when people are talking about the theoretical capacity of these Bandit algorithms, they're simulating like millions of runs, and there's only 40,000 here. So really, how much is it learning? And then especially in our context, it only saw each tutor strategy on average. And when I say saw each tutor strategy, I mean gave it to a student and observed the reward coming in. It only saw each of those like about 6.5 times, which is so little to try and make a decision about, because across these 40,000 recommendations with reward, there were like over 1,000 problems, and for each problem on average like 2.5 to 3 available supports. So it's just this huge breadth of information that it's trying to, without knowing anything about the specific features of this, just say like, okay, I can only learn from experience. What decisions am I going to make? So that's really rough. It's surprising, honestly, that this was a statistically significant accomplishment, but it makes sense that the effect size is really low. It's kind of like, 1 out of every 2,000 times a student asked a problem, they got it right, as opposed to getting it wrong because of our Bandit. So this is not great, but like, oh, it's great for that 1 out of every 2,000 students. But so we want to move on. We want to say, well, okay, if the issue is that we have this huge breadth of student supports and problems and students, why don't we just build a Bandit algorithm that combines insight across all of these different tutor strategies and students and problems and things like that. Yes. Oh, that was the 5 minutes. My bad. So we decided, okay, we're going to make this. We're going to make a decision tree that uses Thompson sampling in its leaves. And we're going to do that because decision trees are nice and easy to understand. And if we want to look inside this later, speaking from like an equity perspective, it would be pretty bad if we don't use demographic data, but I want this to be generalizable for everybody. If you have demographic data and you're using it to make decisions and you don't know how that information is being used to make decisions, then you run the risk of just like, yeah, I've only seen like 10 people of this one particular demographic, but all of them happen to be bad, and now I'm a biased algorithm against these 10 people and anybody else in the future that comes, right? So you just got to be careful. So that's why we went for a decision tree, nice and interpretable. So here's how we kind of smushed together decision trees with Thompson sampling. The decision tree is fit using all of that context. And then during the fitting, in each leaf node, you end up with a distribution of your next problem correctness, or your reward. And typically a decision tree, like for this node in the decision tree, it would just predict like, okay, you have a 50% chance of getting the next problem correct. And here it would say, well, okay, you have a 80, or no, that'd be a 20% chance of getting the next problem correct or something. So instead of just that flat prediction, we just take these two numbers, the kind of counts of the successes and the failures from the training data, and we use that for Thompson sampling. That becomes our reward distribution. And we haven't run it we have since this paper came out, but in the paper, we had not yet run this in ASSISTments, but we did do a simulation using real data from ASSISTments, and we found that usually decision tree Thompson sampling outperforms the standard Thompson sampling, except for the case where I simulate every single day a different group of students uses the platform. So it seems as though information that we have right now, like our context on students, is a lot harder to generalize from. But when I split it up so that every single day different tutoring and different problems are seen by the model, every single like simulated day, because it's simulated over a full year of ASSISTments usage, then it still outperforms. So it seems that in general, it outperforms, and mostly it outperforms because it's able to generalize what's going to be effective across different problems and different student supports, which isn't to say that there isn't useful information in students. It's just to say that the statistics that we have probably don't generalize as well as the other stuff. But it's pretty nice because, we put this in ASSISTments and it's pretty effective, but there are still some problems with decision tree Thompson sampling, which I'll get into. But I also, before I go to that, I want to talk about how just because decision tree Thompson sampling was working overall didn't necessarily mean it was taking advantage of the kind of interactions that we want it to take advantage of. Because like perfect world, there's a group of students that benefits most from one tutoring. It's in that very first diagram, how it's like, the red students benefited most from the orange tutoring, the blue students benefited most from the purple tutoring, but oftentimes it's just that one tutoring is better overall. But we can show that the Thompson sampling with the decision tree was taking advantage of those interactions where it's like one is better for one group and one is better for the other group, because when we fit just a regression model using an interaction of the variables, so if the interaction is statistically significant, then it matters, right? That's something to personalize on. So the statistical significance of those interactions correlated with how much weight the decision tree put on those features. And so moving forward, maybe we can expand these decision trees to random forests because they're just more powerful methods, although we do lose some interpretability with that. Causal forests would be nice because then we could make some causal claims as opposed to just saying like, yeah, the decision tree is better and this is what it thinks, but like I can't give you a p-value on that. And then hefting trees are nice because right now we have to store all the data, or at least the last n data points to train the tree. And hefting trees work from streaming data and just keep statistics in the nodes, and that would kind of help us clean up our database a bit. So with that, I will go to questions. Yeah.
for students.
Yeah.
How sure can we be that the hint that makes the next problem easier is in fact what's best for the student?
It's hard to say. We don't have a lot of like end of year test scores that we can use, but for the most part, I mean, the hints are made by educators trying to help the student. So like when I think about like how could that go wrong, I think of a scenario where the hint is just like the answer to the next problem is 7. But we know it's not that because the people that are making these were given guidelines. This isn't like it's not just open to anyone on the internet to come in and write a hint. Like the teachers whose tutoring is shared by to other students, like anytime we say like, "Oh, you know what, we trust you." That's like a person on the ASSISTments team looking through all their tutoring and going, "Yeah, I trust this teacher." So that's kind of the only way we can really say like at least we're not just cheating the system kind of thing.
Ethan,
Um,
over here.
okay.
Actually, I want to ask a question to my peers because I think we're the major, to my knowledge, we're actually the only major platform that is actually using reinforcement learning in this way, that the software is changing every night. If you know a counter example, please email me.
Okay.
So, quick question. You said that in many cases the best thing was best for all students, but there were a few cases. Do you have any understanding of why some students preferred or benefited more from a specific non-best overall?
Not at all. It's crazy. Like even outside of this work, because this work came out maybe like a month after this system had been running, and now it's been running for months. And what's ridiculous, I don't know if it's ridiculous. What baffles me is that I can look and show that like, oh wow, like 1 out of every 6 students that sees the tutoring is going to do better on the next problem, or like 2 out of every 6 if we're using a contextual bandit. And it's like, wow, that's like a huge impact to students if like 1/3 of them are benefiting from this. Well, 1/3 that actually bother to look at the tutoring, I guess you could say. But then if I say, well, okay, can I find any examples in my data of a statistically significantly better tutoring, or of like a statistically significant interaction between a feature of a student or problem and the tutoring that's picked? And I can't. There's no individual significant interaction. It just seems that these bandit algorithms, because they're making pretty good decisions across all the problems, things are like beneficial overall. But then if I look at every single problem, and I know, I mean, like without hypothesis correcting, I get plenty of significant things, right? But then once I hypothesis correct for the like 300 or so things, then it's like, oh yeah, none of these are actually significant by themselves. So it's weird. I would like to, maybe if we run this for another year, we'll start to have a like high enough end to really find a reason why. But right now we don't.
It's really really cool stuff. I'm trying to wrap my head around um, the factors that you're building that decision tree out of. Uh,
Yeah.
the support features, the problem features. How did you choose those? And is this kind of the size of the tree, or is this an example? And there's a bigger tree, or
Oh no, this
yeah,
is just these. This is an example tree. The real tree is really big.
yeah. So your support features, so you're crowdsourcing hints, for example, right? And then when you talk about support features, you're classifying those hints in some ways. Can you talk about at
Sure.
least that portion
Yeah,
of
yeah.
it, or
I'll talk about all of it.
just to get a sense of how
So
this tree gets built?
student features. I'll just talk about all the features. I'll start with supports because that's the one you care about. Supports. It's all HTML based things that I like extract from the content. So it's like, is there a video? Is there an image? Do they link to an external thing? How many characters are in this hint? How many different messages? Because if it's an explanation, it's only one message. But if it's a hint, it can be infinite potentially, right? So how many messages are there? That kind of stuff. Like, do they use text color, or like do they like bold things? Just basic kind of HTML flag level features. And then for problems, I have all of those HTML features, and I have statistical features. So it's like for every student that did this problem, what percent of them got it right on their first try? What's the average time on task? What's the skill associated with the problem? Things like that. Well, the skill isn't a statistical thing, but there's also the skill. And then for students, I just have those statistics for the student across all the problems they've ever done. So there's like 8 or 9 of them. I think it's in the paper. I hope it's in the paper. If not, it's in the data set that's released with the paper. Oh, but this tree, something, because it's important to point out in this tree, the only time that supports are going to have a different path in the tree is when the tree is splitting on a support feature. Because, you know, every time we use the tree, we're kind of asking it to pick from 3 different things, but we're giving it the same student and the same problem for both of those things. So that's why in this diagram, I show that, like, okay, at the beginning, you know, we split on a support feature and 2 of them go down this way and 2 of them, and 1 goes down this way. But when I split on a problem feature, both go down the same direction because we're using the same problem when we're asking both these questions. Is that good? Okay.
Thanks very much. You said earlier that you did not look at send a student to a different kind of problem. That, you know, you said that just wasn't in the scheme of things. However, could you instrument things in a way to study what happens when the student is working on something slightly different? Because you could, it seems to me that you could get at the sort of the holy grail of transfer. Right? Can they take something that they've learned in this context and get it to help them in this sort of different context, but fundamentally the same underlying concept?
Like instead of next problem correctness, kind of looking at
something,
more
yeah,
detail.
or you know what, it's a yeah.
That's interesting.
I'm trying to get at transfer.
Yeah, it's definitely worth considering. I guess my immediate hesitation to that is the more time between our measure and our intervention, the more other things the student interacts with. Like even just going from one day to the next day, like, all right, the student finished their homework assignment, then the teacher explained the homework assignment, then they learned an entirely new lesson, and now they're on a different homework assignment. So is it our tutoring that helped the student learn, or is it the teacher's lesson that next day, or is it the tutoring on the problem the next? But that being said, like either our noise is coming from next problem correctness not being a very good metric, or our noise is coming from there being more things between our intervention and what we're actually measuring. But like Neil and I have a project right now that we're working on where it's like we agree next problem correctness isn't great, and we're trying to figure out a way to correlate short-term things with long-term metrics that we do trust, like post-tests on whole assignments. And so like if, like, you know, best case scenario, we can just fit a model that predicts your post-test score given like the whole like time series of actions that you take in your next problem. So that way it's still like an immediate thing, but we're kind of using it to predict what they would have done, which who knows if that's actually going to work. But yeah, we do care about that, and that's a great point.
And so we're actually running that study right now. Actually, that's our X Prize competition actually attempt. And so we will see, we haven't pulled down the data and analyzed it yet.
Okay, we have time for one more question here.
You showed in an earlier slide that there was a lot of variability in the hint quality by teacher. Is that a feature you're able to incorporate into your model?
At some point, yes. I think it's not there anymore, but at this time, I think it was. But I honestly cannot remember every single feature. I'm sorry. I think our hope was that while some teachers might be more effective than others, it's probably because something they are doing, not just because of their implicit quality. And that, because the problem with using a teacher ID feature is that that's going to just expand infinitely over time. So we were hoping that, see, now that I'm saying it out loud, I'm pretty sure we don't use the teacher ID, like for that reason. No, we don't. I had to think about it, but we don't use this. Hopefully we capture the variability in our features, and if we don't, then we just need better features.
Great, thank you so much, Ethan. Thank you, that was wonderful.
Thanks, everybody.
Perfect time.